Alright, our next equation is for angle, how much angle is experienced. Now, what we're going to do is we're going to start with this equation. Final angular velocity is equal to initial angular velocity plus acceleration times time. Now, out of all of these, two of them are constants, this one and this one. This one isn't a constant. I mean, we think of it as a constant because it's a final value. But your final value and my final value may be different depending on the amount of time I take. If I take twice as much time, I may experience twice as much angular velocity as you do. And vice versa. If you take half as much time, you may experience half the angular velocity. So this term right here is still dependent on time. It still requires time in it. So it's not considered a constant. It's a variable. It floats with time. If that changes, this changes. Okay, so I'm using that, and I'm using the idea that we talked about before when we came up with the definition, that the angular velocity of an object is equal to the change in its angle divided by time, or expressed in calculus. So now I'm going to do a substitution. You can imagine where this is going to go really quickly. Okay, integration with respect to time plus the integration of omega naught, or angular velocity initial, times time. Oh, I use I for that, don't I? Whatever. Plus that. Oop, one more term. Oh, one more. Not term. Okay, so this is my integration. There's a plus sign in here. Doesn't always come out clear when I do these movies. Okay, cool. Now these cancel out, and I'm just left with this. The integration of that is angle. Now we may say it's angle final. Okay, is equal to, this is a constant, so when I take the integration of that, I'm left with that constant out front, and then the integration of dt, which turns out to be t. Okay, plus this. Well, that's alpha, which is a constant. We've been dealing with that at the very beginning. And the integration of t dt is going to be t squared to the 1/2 power. Or not to the 1/2 power, to the 1/2. Okay? Plus some constant. Okay? Now, moving things around, making it a little more prettier, I'm going to do this. I'm going to have theta final is equal to that constant plus my initial angular velocity times time plus 1/2 my angular acceleration times time squared. Okay, that's how I'm breaking it down as my new equation. I know what's going to affect my final position. I know that my angular velocity will affect my final position. If I have an angular velocity and it's experiencing a period of time, that in that case I am going to get a bigger angle out of it, my final angle, or it may even be smaller, it may be negative. And then any changes in my angular velocity, I'm going to darken that t. It's kind of in that light spot, isn't it? Can you see it now? Yeah, kind of. Okay, there's a T right here if that doesn't come through very well. Boy, not really, but I don't think I can fix it right now. Oh yeah, I can. Here, do this. There we go. Alright, so that's it. But what else affects my angle? What other things affect my angle besides angular velocity, besides angular acceleration, besides time? What other thing affects it? Well, its initial value, where it starts off. So the final expression looks like that. So that's my final equation. My angle final is equal to my angle initial plus my angular velocity initial times time plus 1/2 my angular acceleration times time squared. That's my third equation. I actually lied to you. I have more than just 3 after this. I have a fourth that I need to talk about. But I'm not going to derive one of them. Well, I'm not going to derive a couple of them, but Alright, so there's equation number 3 up in that corner. Cool? Alright, so next one, we're going to do the time-independent equation. I'm just going to come up with it. I'm going to talk about these formulas, and then we're going to move on to the last 3. Okay?